So this is the theory that we've obtained by canonical quantization. And what we'd like to do now is we'd like to work out the equations of motion for this theory. And the way to work out the equations of motion for the theory is by using this boxed equation in green, the Heisenberg equation of motion. So let's start off with I, phi of x and t. And this will be given by the commutator of phi of x and t with the Hamiltonian. Okay, so let's just write this out. So we've got phi of x comma t, then the Hamiltonian, well, it'll be an integral, or there should be an integral d3x, Hamiltonian density of x. I'm going to call this an integral over d3y. And the reason why I'm saying integral d3y is because I can name my integration variable whatever I want, and I want to call it y so that I don't mix it up with the position of my scalar field x. So it'll be an integral d3y. I'll have 1/2 pi squared at y and time t plus 1/2. I'll have the gradient of phi dotted into the gradient of phi, also at y and t, and then I will have plus 1/2 m squared phi squared, also at y and t. Good. Now, look at the commutators, and what you can see is phi commutes with phi. Because of that, there'll be no contribution from this gradient of phi dot into gradient of phi term. That'll just commute with phi. And there'll be no contribution from the phi squared term. That'll just commute with phi. So all that we need to do is calculate the commutator of pi squared with phi. Now, you know how to do that. As usual, we would simply use the product rule. So this is going to be equal to, I'm going to take the 1/2 and the integral d3y out of the commutator. And then what would we have? Well, first, by the product rule, we commute phi with the first pi. And we leave the second pi alone. Plus, now we leave the first pi alone. And we calculate the commutator with the second pi. Good. Now, what is this commutator equal to? Well, there it is in the blue box. It's minus I h bar delta of x minus y. I'm not going to keep the h bar anymore, so let me just set h bar is equal to 1. And the delta function, of course, is a number, so it commutes with pi. So the two terms inside the bracket are going to be identical. I'm just going to write one of them, and I'm going to drop the 1/2 up front. Okay? And then I will have minus I. I said I'm going to set h bar to 1. I've got delta x minus y. And then we've got pi of y comma t. Oh, now the commutator that I want is the commutator between phi and pi. The commutator that I've quoted is the commutator between pi and phi. So to get the phi pi commutator from the phi pi commutator from the pi phi commutator, I need to change the sign. So this sign over here actually needs to be a plus sign. Integrating over the delta function, well, that'll just set y equal to x. So I'll end up getting I times by the pi of x comma t. So what did this Heisenberg equation of motion tell me? It told me I phi dot of x comma t was equal to I pi of x comma t, which means phi dot of x comma t is equal to pi of x comma t. So that's what the first Heisenberg equation of motion tells me. Good. Now let's look at the second Heisenberg equation of motion. We can calculate what is I pi dot of x and t. And this time derivative will be given by a commutator of pi x comma t with the Hamiltonian. And I'm again going to write the Hamiltonian in terms of the Hamiltonian density. And I will again call my integration variable y so that I don't mix up my integration variable with the position of my conjugate momentum. So the first one will be a half pi squared of y and t. Then we'll have plus 1/2. We'll have the gradient of phi dotted into the gradient of phi of y and t. And then we will have plus 1/2 m squared phi squared of y and t. Good. Now, this time, pi commutes with pi, so the commutator of pi with pi is 0. So that means when calculating this commutator, we can neglect the pi squared terms. The remaining two terms are rather straightforward to compute. What do we need? Well, we need the commutator between pi of x comma t and phi of y comma t. So I'll just put this one here. This is minus I delta of x minus y. Okay, so that one you know, that was straightforward. But we also need the commutator of the gradient of phi. And let me be very explicit. These are derivatives with respect to phi, with respect to y, of course, because phi is evaluated at y. We need commutators of the gradient of phi with pi. And to get that commutator, you just take the commutator that you've got and you act with nabla acting at y. Okay, so acting with nabla, well, nabla doesn't touch pi because pi only sits at x, but it does act on phi. So that's what we get for the left-hand side. And then the right-hand side, we just get the gradient of the delta function. Now, we've been careful to track that things depend on, that the nabla depends on y. Why is that? Well, you know, the delta function only depends on x minus y. Because of that, nabla acting with respect to y on the delta function is minus nabla with respect to x acting on the delta function, okay? And that's because the delta function is a function only of x minus y. So we need to be careful about which variable we're differentiating with respect to. Okay, so now let's write down what we get for our commutator. So this was all part of an aside. This is just some results that we're going to use. So what do we get now for this commutator? Well, the 1/2s will cancel because they're two terms, just like we saw for the calculation that we just did. So I'm going to be a little bit quick, but you can check it in detail. We will get commutator of pi of x and t with the gradient of y. In fact, sorry, I'm even going to write in this commutator, okay? So let me just erase this. So the commutator of pi with the phi gives us minus I, the gradient with respect to y of delta of x minus y. So this is the pi with the gradient of phi, and then we've got the second term, so this is dotted into the gradient of phi of y comma t. Oh, and I do need to not drop my integration with respect to y. So let me just move this over. Good. And let me put in the integration, d3y. And then we need the m squared term, and the commutator here is just minus I delta x minus y, and then we will have phi of y and t. So to get this result, all that I have done is I've used the product rule again, and I have used the commutators shown in the black box on the screen. So now we want to integrate over y, and we will do that in a minute.